Hello there. We're just starting in again with the third in a series on rotating reference frames from Newtonian Mechanics. And so this time we're going to look at Coriolis Acceleration, which is the third part of a rotating reference frame on the surface of a sphere, specifically Earth we're using for now, but we can always look at it from any rotating reference frame on the surface of anything. So let's actually go back and review our equation that we looked at, that we derived in the first video and manipulated the second term in the previous video. And what we're looking at here, again, just to review, is on the left-hand side of the equation is the effective force in a rotating reference frame equals due to a true force, some Newtonian force which obeys all three of Newton's laws. And then it's adjusted by these other two, which are effects directly related to the idea that you're doing your measurements in a rotating reference frame. So the F is a true force. It could be anything. It could be a tension. It could be a gravity. It could be any set of forces that causes masses to move, which also obeys Newton's third law, which is equal and opposite reactions. The other two components on the right do not obey those laws, and so we typically call them fictitious or pseudo-forces. But in this sense, they actually cause a real thing, so that's a very bad term. I hate that word, fictitious force, because these effects are real, so it's not fictitious. They just don't obey Newton's third law. So we can call them non-Newtonian if you like. Anyway, so what we're looking at is the Coriolis acceleration, and that is, or the force in this derivation, as you see below, that would be a force version. But previously we were looking at the centrifugal acceleration, which is the middle term. Now we're going to look at the second of these, the Coriolis force. And this thing only affects things that are moving, not stationary. So if something is not moving at all, if it's stationary, in a rotating reference frame, it does not experience an acceleration. The mass m does not experience an acceleration. So there's the big omega, which indicates a vector of rotation about an axis, and the v tick means we're measuring the velocity of something as measured in the rotating reference frame. So let's look at these reference frames again. It's the same thing we did in the previous two videos. We're looking at our rotating reference frame is Earth, which is a sphere that happens to be rotating on its axis. It's not flat. So the Earth has the equator, and the rotation axis is the North Pole through the South Pole. Rotation axis, not the magnetic pole. And once again, we're indicating that by a green vector that's poking up out of the North Pole, and we're rotating a little line around it to indicate that that is its rotation direction. But we could always assume a right-hand rule, which is our standard assumption, and say omega with an arrow across it is a vector that is a rotation vector, and it's pointing in a particular direction according to a right-hand rule. And what do we mean by right-hand rule? So take that green arrow that's pointing up to that little dot, the dotted green arrow that's pointing up to the omega arrow, the omega vector, and think of it as your right hand. Take your thumb at arm's length, put your thumb up, and curl your fingers around. The curl of your fingers around your thumb on your right hand indicates the rotation axis. If we're doing a right hand rule, which is very standard, which is what we always use for rotation, that's a standard across all of physics, is that we have a right hand rule. And so as you curl your fingers around, if it's going in that direction, that curling direction, knuckles to fingertips, then the thumb is pointed in the direction of the rotation axis, and that's the direction of the vector. Okay, the inertial reference frame, the Newtonian inertial reference frame, is the center of the Earth, and we're using as vertical up towards the rotation axis, one of the things, and along the equator, and then out of the screen for the third of the axes. Then it's separate. Then the rotating reference frame itself is offset from the inertial reference frame on the surface of the sphere by the lowercase r vector that goes to the surface. It just so happens to be the same as the radial vector, capital R, at the lower left. But in this case, it could be above or below. You could drill a hole down beneath or fly a plane above. That would be the little r. But right now we're going to make them equal just to make things a lot simpler. And so that little r is at some latitude from the equator. And the rotating reference frame is defined, of course, to have z being straight up, x being pointed towards north, and y being pointed towards the west. And that allows us to have a right-hand rule of x to y to z. Okay, so there's our rotating reference frames, and so now let us consider only the effect. We're going to ignore the centrifugal acceleration at this point, but now let's consider the effect of some mass m falling under the force of gravity in that rotating reference frame on the surface of Earth. So we define those Cartesian axes as above, so there's our z-axis up and x, y, horizontal, and so forth and so on. But we can now deduce that the Cartesian equations of motion, using the cross product that I defined and talked about in a greater extent in the previous video, we can use the cross product of omega cross v, and to notice that I've gotten rid of the masses there because F equals ma, and mass and the acceleration here is the acceleration only due to gravity, and that's what the G arrow tick. G arrow tick is the effective gravity as seen on the rotating reference frame, as measured on the rotating reference frame, and that's equal to the actual gravitational acceleration in the inertial reference frame, and then it's adjusted, or there's a part that's subtracted, and that's twice the rotation vector cross product with the velocity in the rotating reference frame. So go back and look at my previous video on the to learn how to actually what the cross product is. But if we plug in all the numbers, and there's our little vectors are giving the most important things on the lower left there, kind of smallish, but we can see that the cross product, the v sub z, z's and y's and x's, those should really have ticks on them because we're measuring them in the rotating reference frame. But the cross product works out to be this. I've included the zeros that we see from the two vectors that we're looking at. Now the velocity can be in all three directions, x, y, and z, x being north, y being pointed, the y vector, the zero of it being pointed due west, and z being pointed due up. So that's why the g is negative, because it's down. And as well as the other part of it too. So let's collect all these terms and just look at the accelerations of each, and that implies that, I've changed my notation a little bit too. So the dot over a given variable indicates a derivative with respect to time, and that's what the dot triple bar equals d over dt is to be indicating. So if you got two dots, it's two derivatives, and a single dot means one derivative. And we have the effective acceleration in the x direction, which is just one of the three components of the g-tick arrow in the way upper left there. So that g-tick arrow has three components, one in each direction, and we add them together to get the total vector equation. And these three components are, one in the x direction we have just something associated with the latitude, which is that sine of lambda, and of course you have the magnitude of the cross product there too. The y vector is dependent both on the latitude in two ways. One, and you see these things are dependent upon each other. So the acceleration in the x direction is dependent upon the speed or velocity in the y direction. And the acceleration in the y direction is dependent on the speed in the x direction and the speed in the z direction. So that's interesting, isn't it? So the z direction hat is essentially Vx hat. See, if you look closely, I've just translated V sub z into z dot tick. They're the same thing. So from the first equation, V sub y is y tick dot, and V sub x is x tick dot below. So that's what the transformation I did between those two sets of equations is. And so I've broken them out from that parentheses notation to making it three specific equations, each for each component. And so those dots indicate derivatives with respect to time of a given variable. So they are measurements in the x, y, and z direction, but they're all measurements of velocity and acceleration. That's all we have there. So I've also neglected the centrifugal acceleration just to make this simple. Well, I really want to be able to do that. Just like we did, we're breaking things down. And so I've also neglected air resistance, which is a big thing. It's much bigger than the Coriolis effect. So Coriolis effect is nullified by that. And Coriolis effect is really small. It doesn't work in your bathtub. Sorry, that's just too bad. It doesn't work in your bathtub. You do not see the Coriolis effect. That is due to the simple design of the tub and the design of the pipes. Okay, so I'm just trying to keep things simple, as you can see. And if we really want to do this, we can imagine that there's no air resistance, and so we could just get rid of all the air on the Earth and everybody has a bad day. But now let's not talk about that, because let's have a good day. So let's actually then manipulate these equations, and we'll now consider a particle. And we've got to take this equations of motion and do something. So far they've been exact, but now we're going to start to make a series of approximations in order for us to understand and better understand, to understand the Coriolis effect as well as its magnitude. So let's just now take something and simply drop it from a height and just above the Earth's surface, so it's going to be dropping, say, but the height that it's dropping from is much smaller than the radius of the Earth. And we're also going to assume that the Coriolis force is a much smaller effect than the force of gravity, which it is. Therefore, and this is where a lot of people will get bent out of shape, you can treat this thing as a very small parameter. And to lowest order, what do we mean by lowest order? It means we're taking a Taylor expansion, and the Taylor expansion, we're getting rid of all of the terms that have powers of omega that are, well, 1 or greater in this case. So we're just getting rid of it. But that's what we mean by lowest order. You can take any function and turn it into a polynomial expansion. Some are finite, some are infinite, and those are, and we can then say a function is a series of polynomials, and they are in higher and higher orders of magnitude. So when we say the orders of magnitude, the equations above would have some values of the magnitude of omega, and that omega would be in the cosine would be 1 plus the cosine of the angle squared, or the angle squared over 2, I believe it is. Yes, it is. And 2 squared over 2, and so on and so on. So we're going to get rid of it because we don't care about that, because it's very small. So therefore, we're approximating the acceleration in the z direction to be only due to the acceleration due to gravity. Now, we're okay in saying that because the deflection that is implied by that z double dot is small, and we're going to see that below very shortly. So is z tick, then we can simply integrate, if we continue down this parameter of this direction of saying that omega is small compared to the Coriolis force is small compared to the acceleration due to gravity, then we can say that z double dot tick, meaning the acceleration in the z direction in the rotating reference frame, is just that of gravity, of the real gravity. So it's an approximation. I shouldn't use an equal sign there. It's an approximation, but we're going to keep it as an equal sign just because. But I just want to make sure you know what we're doing here. And you can integrate that in a standard way to get the equation below for z tick, and we see that it's a time squared. So let's go and manipulate that and use this to our advantage, so we can substitute that z equation into the other ones. And now we have neglected on the lowest order things that are omega, and we neglected that only in the z because g is so much bigger than omega that it just doesn't, we don't use it, but we will accept it in the other two. But we're also going to say that since it's small, we'll only keep omega to the first power in things that are also small. So if you have something that's small, and it's compared to something big, you can get rid of the small part, so because the big part is big. But in this case, so therefore in the z, the big part is gravity, and the small part is that. But in the x and y components, the big parts are the omega are the omegas, and the small parts are anything that would be omega squared. So we can approximate all of these things using Taylor expansions, etc., in order to get the equation below. And that's what we're left with, which is these very simple equations that look quite interesting. Notice that x is not going to have a north-south deflection, but it will have a deflection that looks like it's going eastward, because y is defined to go to west, and the negative sign would then make it go east. And it goes by the time cube, which is fascinating. It also depends on the latitude, and it depends on how fast the thing is rotating. So that's an approximation. So the particle would be deflected eastward, and it would hit the ground roughly at the time of 2 times the height divided by the square root of gravity, square root. That'll give us the height at which it gets to 0. And therefore, the net eastward deflection as it strikes the ground is seen below. Now, if you look closely, that's not big. So it's not a large deflection. And that's an important thing to remember, because this deflection, let's see how big that would be. And so it's in the same direction as the Earth's rotation, meaning going from west to east. It is biggest at the equator when cosine of lambda equals 1, and it's nothing at the poles. So cosine of lambda at the poles is 0, so there is no eastward deflection. But I guess there's no such thing as deflection at the pole of east anyway at the poles. But it's so small that we can say that if you drop something 100 meters, which is, I guess 5, 10 stories or something, an 8-story building, 100 meters, it deflects by 2 centimeters. And that is 1 meter. It's 2 centimeters is 2% of 1 meter. So this is 2% of 1%. So this is a really small effect. It is measurable, but it's small. So therefore, we are justified, given the result that of our assumption that the Coriolis effect is small compared to the gravitational effect. So to the lowest order, we're okay. If we really wanted to add in and go back to those equations and say we're not going to approximate it, we're going to plug it into a computer and do it right, quote, do it right, you wouldn't get too much of an adjustment. It might be 2.3 centimeters, it might be 2.22 centimeters, it might be small, but it's not going to be a huge adjustment from 2.2 centimeters. So therefore, that's why we bother with these kinds of approximations in physics, because that helps us do something and get something a little bit better than that, and not give us such problems with computing power and trying to write that program in Python or whatever you want to write it in, MATLAB, it doesn't even matter, or Java Basic or JavaScript or whatever you want to write it in. But you don't have to if you have a good set of approximations that leads you to a place, and as long as the end result makes sense. See, we would have to go back to the drawing board and say, we got to look at it better. If the deflection was like 10 meters, that's pretty big, and that would be something we would want to look more closely at, because if the deflection according to this was 10 meters, then the real deflection might be something on the order of 20 meters. And that's enough to say, okay, we should probably have that. But reality is that Coriolis effect is small, and therefore our justification for these approximations is a good one. So let's continue on with this idea, and now let's think of a particle that is launched horizontally with some really big velocity and no up and down motion. So this is really going fast. It's going to skid across some pavement or something, because gravity pulls things down, but let's just assume that it's launched horizontally and it's going to go across the surface of the Earth. Maybe we're just launching it horizontally on an ice sheet. So we're doing a very high bullet on an ice sheet. Well, that's kind of a scary thought. But now we're also going to define the compass bearing, theta, which is that Greek letter theta. And so we have the x direction is cosine of theta, which would be up is 1, and to the east is 0. But so north is 0 degrees and east is 90 degrees, etc., which is kind of what you think when you look at a map. And so we've defined previously, in the previous thing, when we defined our Cartesian system, we defined it not map-wise, we defined it kind of looking up-wise. But this is actually more looking map-wise. So, which is important, because historically, and people kind of look down on maps. So let's see how we do things. So we're going to do the same kind of derivation before. We're going to neglect vertical motion because whatever, but we'll also take things, and so we're also going to make sure this is without vertical isolation. We're also going to assume that omega is a small value compared to the force of gravity. So let's keep going down that path, and we find that we get these particular set of equations. So this is where we're going to be deriving. We have these things now to approximate it. So our velocity is this. We now have no z component. We're neglecting all vertical motion, and we only have an x and a y components. We only have an acceleration. We have a deceleration in x and y. That's interesting. Okay, so let's look closely. And we can integrate those two things above to get the velocity components, which we kind of had before, but now we have the velocity that's changing. So we had an initial velocity, which is on the left-hand side of after the approximation. But the right-hand side comes about because we're integrating with respect to time for the change in velocity due to the Coriolis acceleration. And so we look closely at this and we say, wait a second, there's a value that's happening here, and there is a change in the compass bearing. So we see that it's dependent upon the compass bearing, so that looks awful lot like a rotation. So let's see how that works. All right, so that equation is kind of gnarly, but we can do some simplification by remembering some 10th grade geometry. We can use these sine angle plus angles, and this is going to be really helpful because if we look closely, we can use all this mess, those particular things, and we can say, wait a second, we can pull out the v. We can pull out the v. That's easy enough, and we're left with cosine theta minus something else, so minus 2 omega sine theta t. But let's see if we can make that even easier. But if we apply this formula, we get the following. X dot looks like v naught cosine of the sum of those two things. So look closely at these equations, and we see that we can substitute in and get rid of the small bits. Now, cosine of an angle is like 1 plus omega squared, angle squared. And sine of an angle is like angle plus angle cubed. So we don't care about the angle squared, and we don't care about the angle cubed. We only care about ones and angles. And 1 is bigger than the angle, so that's how we get the equation for x dot below. So you'll notice that the omega sine lambda part of the cosine a plus b disappears because it's small compared to the other. Because it's cos, cosine of cos A plus cos B equals the cosine A times the cosine of B, and here B is 2 omega sine lambda t. And we just plug these things in, and if you use the small approximation saying that theta is greater than 2 omega sine lambda t, and very specifically lambda squared and lambda cubed are going to be things that we ignore. So therefore, anything like cosine of omega sine theta simply becomes 1, and anything like sine of 2 omega sine lambda just becomes 2 omega sine theta lambda. So it doesn't. We're left with the actual thing. We're actually left with those variables, and we can have this nice little approximation, which then ends up looking like this. Therefore, we have the same angle change in both the x and y direction. One is negative, one is positive, so therefore it's a rotation. And the rotation rate is the change in theta with respect to time, which is approximately, now we're just going back and making sure we establish this approximately, because these are approximate, 2 omega sine lambda. Now we could go and do a full numerical analysis on this, and sure, we get slightly different results, but not by much. So the rotation would then be clockwise, looking down from above in the northern hemisphere, the counterclockwise in the southern hemisphere. There's no rotation at the equator, and there's the most rotation at the poles. That's interesting. All right, so let's continue on. And we see then that the Coriolis force is very significant. We see it all the time. It's a part of our weather patterns. Therefore, the intense heating at the Earth's surface near the equator, where it gets almost all sunlight all the time, results in hot air is rising up. And so hot air rises. Cool air then goes in from the north or from the south in order to fill basically the flow where the hot air is rising up, and that hot air then flows north. So you have this circular flow that happens at low altitudes in general from north towards the south, and then from the south towards the north in upper latitudes. And these are called trade winds. And so the Coriolis force deflects the moving air that happens due to this exchange of heat between the equator and the lower atmosphere, the equator and the upper atmosphere. So therefore we get hurricanes. And hurricanes means that the cooler air is moving northward in the southern hemisphere, and the cooler air is moving southward in the northern hemisphere. And the Coriolis effect deflects it, and we get the trade winds, which are indicated by these arrows. And westerlies move from the west, and easterlies move from the east. So you can consider them like they don't really have easterlies. So we have these three different things. So the trade winds are due to the fact of the change in the heat transfer. Okay, so what does this end up making us look like? So the Coriolis force drives these cyclonic rotations that we see. So when we say that the Coriolis acceleration is a fictitious or pseudo-force, we don't mean it doesn't exist. We just mean it's not a Newtonian force. Cyclonic action and rotation would not happen if the Earth were not rotating. And specifically, the shapes of these things wouldn't have their shape if the Earth wasn't a sphere as well. So there is just the existence of the rotation of the Earth is seen because of this. So, flat earthers hate them. But anyway, we keep going. These tropical storms, there's a series of them, and cyclones. I believe this is I forget which type. This is a definite hurricane season. That's a big old hurricane going across Cuba. And there's one developing or crashing into the Gulf there. And there's another one right behind the other hurricane coming right up. So this cyclonic rotation is evident in the Coriolis force. But it's not part of your bathtub. Notice the center of the hurricanes. There's a large area where we do not see any motion. In fact, it's well known that inside the center of a hurricane, it's calm. So right up to that point, the wall of the eye of the hurricane, it can be quite violent weather, but once you're in the middle of it, it can be dead calm. That doesn't mean that you have a dead calm you do have a dead calm in the center of your pipe as you're draining out of your bathtub, but that's due to the shape of the pipes and the shape of the tub, not due to Coriolis effect. Anyway, so we will leave that here, and there's a bit more on the Coriolis pseudo-force. I'm going to leave it with pseudo-force. I hate fictitious force, but we'll leave it with pseudo-force because it doesn't obey Newton's third law, meaning there's not an equal and opposite reaction, meaning this cyclonic rotation doesn't twist the Earth the other way. That's what we would mean. So if the Coriolis force were a true Newtonian force, that action of rotation would actually cause a twisting motion on the Earth in the other way to something that couldn't push back. And in fact, if you would say, well, what would be the natural thing? Oh, you got a cyclonic rotation in the atmosphere. Maybe the ocean would rotate that way. But no, the ocean just also gets swept up in the air rotation. You can see waves moving that way, but they don't push back against it. There's no friction between I guess there is, because there's no friction that pushes against that. And that is, well, I guess if you look hard enough, you can find it, but the rotation of the Coriolis force, and by rotate, look for it hard enough, we can find it, we mean that air does have friction against, when you hear the wind howling, it's because the molecules of the air are rubbing up against something like a building or a mountain or whipping waves up. And yes, that's causing friction, and yes, that's dissipating energy. But it's not like it's actually having something that pushes against, where there's an equal and opposite reaction. There is no equal and opposite reaction that happens due to this hurricane. So there's the Coriolis effect pseudo-force on it that is strictly due to the fact that the Earth is rotating. All right, so next time we're going to be talking about the Foucault pendulum and how we can see that the Earth is rotating without satellite technology. We can just simply have a Foucault pendulum. A pendulum is a specific thing that says, yes, the Earth is rotating. We can, if we have a satellite looking down from orbit, we can certainly see that. Also, we can see the Earth is rotating if you happen to go be on the moon and look back and see it. So there is a bit more about our rotating reference frames. We've derived the equation in the upper left. We've also looked now at the centrifugal acceleration, which is the second term, and the Coriolis acceleration, the third term. So we're going to put some of this together to look at the Foucault pendulum next time and see how we see that the Earth is rotating.